Good afternoon, and welcome to the Mike Korchynsky Memorial Symposium, and we're all glad we can be here and remember all the work that Mike has done. I myself spent 15 years working with him with Strategic Minerals Corporation and have many good memories. And in fact, the basic talk that we have here is based on the things that he started, and we will go through those as we go. And I was just adding my particular changes to it to hopefully be helpful to the metallurgist who's out actually trying to design alloys, the hot mill metallurgist, the product metallurgist that's trying to determine how much vanadium, will vanadium work, and how much do I need to add to be able to meet the property requirements of the specification or the customer. So hence the title is an updated prediction model for vanadium precipitation strengthening of ferritic steels. Early work on prediction of vanadium precipitation strengthening was often complicated by the lack of recognition of the effects of heat treatment and nitrogen content. As with all microalloys, vanadium must be in solution in the austenite prior to transformation for effective precipitation strengthening of the ferrite. And results from normalized steels exhibited very different vanadium strengthening effects when compared to as-rolled steels, and often nitrogen contents were not considered. This resulted in some somewhat different perspective of what the strengthening effects of vanadium additions were, certainly some confusion and misinterpretation of data that was available. Grozer in 1975, microalloying 75, the Symposium really started microalloying, which Mike Korchynsky was a very prominent contributor to. In that conference, Grozer presented some of the first results of extensive production of vanadium strengthened hot rolled strip steels. In there, a graphical model was used to describe the effects of vanadium and nitrogen on the as-rolled yield strength. This strength model was first published by Korchynsky and Stewart in 1970. Also presented in that conference was a graphical representation of the effect of coiling temperature on vanadium nitrogen strengthening, which has been widely referenced by subsequent researchers over the years. This is the graph first published again by Korchynsky and Stewart, showing the strengthening effect, that is the increase in yield strength as you see on the left, for various nitrogen levels, for increasing nitrogen levels for 3 different levels of vanadium addition. This again is quoted widely, cited widely for over the years as being the first real representation and information to the industry that the vanadium nitrogen system could be very effective. This is the effective coiling temperature graph that was also included, and again shows the relative effects of nitrogen levels on vanadium bearing steels. Again, widely used. But the problems with this graphical model, this is the first graph that I did show, included a number of things. First, there's no vanadium strengthening apparent at 0% nitrogen. In other words, hypothetically, 0 nitrogen steel would still have some strengthening from a vanadium addition because presumably carbon would be available interstitially. But in this graph, it doesn't represent that. It all starts from the 0 point. And forcing these curves to start at the 0 point causes the nitrogen strengthening slopes to be considerably different depending on the vanadium level. The nitrogen strengthening rate, therefore, varies significantly at these different levels, which isn't necessarily consistent with what subsequent research has shown. And it also fails to quantify vanadium strengthening, which is the primary alloy being used by the metallurgist in their alloy design. They need to know how much vanadium do I need to get to the strength that I want. And it's difficult to tell from this curve simply because vanadium content is not one of the variables of the graph. Subsequent to that work, there's been much more work I will refer to the work by Savecki and others on nitrogen, the effect of nitrogen on precipitation strengthening. In this case, a 12 carbon 135 manganese material, as you see, with aluminum and 09 vanadium. In that case, the graph clearly showed that there was a linear strengthening response to the increasing nitrogen levels, and that this slope was consistent with different processing variables, which changed the absolute strength level, but the strengthening increase from the nitrogen contribution, as you can see, as we go from 05 to 120 to 180 region, that strengthening contribution was consistent across all of these processing and cooling rate conditions. And this rate of strengthening was about 7 megapascals, or 1 KSI in the inch-pound units, per 10 ppm nitrogen added. It turns out that this number has been repeated time and time again by multiple researchers and also many commercial applications of this alloy system, that this 7 megapascals increase in strength for 10 ppm nitrogen added, as long as it's substoichiometric to the vanadium nitrogen stoichiometric ratio. The objective for improving the model then was to develop a descriptive graphical model of vanadium nitrogen strengthening that would have visual impact for sure, and also that vanadium should be the primary variable, so you can then quantify the relative effects of vanadium and better design your alloy content. And it should also reflect all strengthening possibilities, and those include vanadium nitride precipitation and vanadium carbide precipitation, and of course, therefore, has to be a function of the presence of both interstitial nitrogen and carbon. Data used for model development included this information. I don't intend to go over that, just to show you roughly the kind of information that's available, that was available. It is not intended to be analytically rigorous, but simply to generate a descriptive model that could be used across many different applications. The regression results, as shown, again, were not necessarily rigorous, but they were compared with many different actual production data sets and found to be very descriptive of what is actually being observed. And it also agrees with this 7 megapascals per 10 ppm nitrogen level addition that would be expected to get with the nitrogen assistance to the vanadium precipitation. You also had to develop this model, had to develop some prediction of what the effect of interstitial nitrogen might be without precipitation. In other words, if you have nitrogen without vanadium, what kind of strengthening could you get? We used the model that was suggested by Pickering, as you see here. I think subsequent to this, there is strong evidence that says that model probably underpredicts the interstitial nitrogen strengthening component, but nitrogen strengthening, interstitial nitrogen strengthening is not something normally would be recommended, and so it's not a major issue with the predictive model. Using that regression work, you can have this initial literal interpretation of what it's trying to tell you. What do we know for sure? That there is a relatively small contribution to the nitrogen interstitial strengthening, which is actually would be the separation of the first straight lines, as you see right here. Interstitial nitrogen would separate those lines, that is, the higher nitrogen containing line would have a higher starting strength with 0 vanadium compared to the lower nitrogen levels. There may be more increment than what this graph shows, but what it does show is that as you add the nitrogen, as you add the vanadium, excuse me, there's ample nitrogen to combine up until the point you reach the stoichiometric level of vanadium to nitrogen in the system. So vanadium nitrogen strengthening occurs at the highest rate. The rate of strengthening, as you see, is the steepest slope. But eventually, you do run out of nitrogen. And that vanadium nitrogen ratio stoichiometrically is about 3.68 to 1. We use about a 4 to 1 rule of thumb for that design. But as you can see, at 50 ppm nitrogen, you will run out of nitrogen at a fairly low vanadium content, something on the order of 0.25, 0.3 vanadium. As you go higher in nitrogen, you still eventually leave the point at where you are past the stoichiometric ratio of vanadium to nitrogen. Even at 200 ppm nitrogen, there is no more significant nitrogen left after about an addition of 0.08. That, of course, is assuming 100% precipitation of vanadium nitride, which isn't necessarily true, and we'll talk a little bit more about that in a little bit. After you run out of nitrogen, then you get vanadium carbide precipitation strengthening, which not so much because the precipitate itself is any different, but the formation of the precipitate is much slower and tends to be coarser and less effective in strengthening than the vanadium nitride. So it continues to strengthen, but at a somewhat reduced slope. So once you essentially have exhausted the available nitrogen, now you're strengthening with vanadium carbide precipitation. Now, there can be many different carbon levels of steel that you can use this system with, but we have to remember that it's only the carbon in the ferrite that will precipitate and give you vanadium carbide strengthening. Precipitation of vanadium carbide in the austenite, if it happens, which is is not particularly likely anyway because of the high solubility of vanadium carbide, but even if it did, it would not contribute to strengthening. So you have the first slope, which is vanadium nitrogen strengthening. The second slope is vanadium carbide strengthening, but we have to remember the maximum solubility of carbon in iron ferrite is about 0.02%. So you can also run out of carbon. So eventually, stoichiometrically, you will run out of carbon as well. So you first can form vanadium nitride, then vanadium carbide, and then there is really no other interstitial element left for the vanadium to precipitate to contribute to precipitation strengthening. So it simply stays in solution and the precipitation strengthening component essentially stops. Now looking at that literal model, as I called it, and comparing it to the Korchynsky model on the right, you can see at roughly the same axis of yield strength increase on the left, that in fact they're very similar. Of course we have now exchanged we put vanadium content on the lower axis rather than nitrogen content, which then allows you to be predictive in how much vanadium you want to add, and we do that at various nitrogen levels to give you an idea where you need to be with nitrogen content when you're done. As you can see, the more vanadium added, the more nitrogen is needed to make maximum use of the vanadium that you have. Some important points from this vanadium strengthening graph is, again, it provides a quick method to estimate vanadium requirements based on incremental strength that you are looking for. Demonstrates the importance of managing the nitrogen level. It reaffirms the fact that precipitation strengthening requires both vanadium and either carbon or nitrogen to be effective. Carbon availability is limited by the solubility in ferrite, and typically that's a 0.02% max. Nitrogen availability is, of course, limited to what effective nitrogen is level. In other words, it's not necessarily just the total nitrogen, because other elements may combine with the nitrogen prior to it being available for vanadium nitride precipitation in the ferrite. These elements that in fact do compete with vanadium for combining with nitrogen are titanium, aluminum and niobium. For valid application of this model, we have to keep certain things in mind. You have to be looking at a situation where all precipitates must be in solution in the final reheat. That means the reheat temperature should be high enough to get all of the microalloys in solution, certainly all the vanadium in solution that you're looking for the precipitation strengthening. However, things like titanium, you may never get back in solution once the steel is solidified. But it does mean that probably has to be a reheat temperature much higher than a normal austenitizing temperatures for heat treatment, such as normalizing. So when you normalize material, you can't expect to get the kind of response from vanadium nitrogen precipitation strengthening as we see in this model. It pretty much limits the model to use in as rolled or as forged conditions. But that is primarily where microalloying is used. So it's really not an issue, you just have to be aware of that. And also, no significant precipitation should occur in the austenite prior to final transformation to be able to get this precipitation strengthening. The final microstructure is a ferrite pearlite microstructure. Final precipitation in ferrite continues to a comparative level. In other words, the processing should be very similar, and then the similar cooling rate after the transformation has completed. And all nitrogen that you presume to be part of this model is in fact effective nitrogen. That is, it is available for vanadium nitrogen precipitation. Carbon availability in ferrite is generally limited to 0.2%, but we will talk about an example where they may be higher than that. This, in fact, is that example. It's work done by Zajac, Savecki, Hutchinson, Langenberg, that proposed that at intermediate carbon levels in the 20 carbon range, that during cooling through transformation, you can, in fact, get a supersaturation of carbon in the ferrite. And that's represented by this Solvis line that shows the equilibrium between carbon in ferrite and austenite to the right versus in this case, where then you, in fact, reach higher carbon levels in the ferrite than you would if you simply have a equilibrium between the ferrite and cementite that normally forms during the transformation of austenite to ferrite. So you get an austenite pearlite kind of structure, but with higher carbon levels, you can have higher hardenability, therefore lower transformation temperatures, potential supersaturation of carbon in the ferrite, and therefore a higher driving force for vanadium carbide precipitation and more carbon being available. As a result of this supersaturation of carbon in the ferrite, you may extend the vanadium carbide strengthening component to higher vanadium levels. So the rate of strengthening, though, will still remain the same as shown in that curve, but and the higher nitrogen strengthening component, the 7 megapascals that we quote, is still relevant and is still appropriate for these intermediate carbon levels. The differential increase that you can get with nitrogen, as long as it's substoichiometric to the VN ratio, is always consistent at this near the 7 megapascals if appropriately processed. This is a representation of what we expect to go on. There are a number of things one can conclude looking at this particular kind of this information. Obviously, this is a isothermal transformation diagram of a plain carbon steel showing formation of both the interphase precipitation of vanadium carbonitrides and the general precipitation of vanadium carbonitrides here on the right. The temperature for interphase is higher, the random precipitation is lower. One of the things we've seen with this modeling is that it really isn't critical whether the precipitation is interphase or whether it's random. It still quantitatively contributes to strengthening at about the same predictable rate. However, in looking at this curve, we have to it does remind us of a couple of things. One is that precipitation in the austenite that is prior to reaching this transformation lines, that up in this zone does not contribute to strength. And the second is that the precipitation occurs, strengthening does occur at a relatively high temperature. And there is a temperature below which this precipitation of vanadium carbonitrides will cease, and you no longer get any effective strengthening if it has not precipitated at the appropriate time. Typically, most researchers under looking at production kind of processing times and temperatures find that anywhere from 50 to 70% of the vanadium will precipitate if there's ample nitrogen available. If it's only carbon available, typically that number is less than 50%, maybe 20 to 40. That is the primary reason why you see the differential strengthening rates between the vanadium nitride and the vanadium carbide. And then finally, we know that nature doesn't work in straight lines. It definitely works in curves. And in fact, if you tried to generate this model based on actual production data, it would be very difficult to actually determine where these inflection points are from vanadium nitride to vanadium carbide to vanadium nothing, because there's nothing available. What you will see is more or less a continuous curve that's gradually approaching a zero strengthening rate. And these inflection points are rounded off in this graph to better represent and to better estimate what you actually will see when you start doing alloy design based on a vanadium nitrogen system. So the intent of this representation is to provide information, usable information, to those alloy designers out there that want to use vanadium in the most appropriate and cost-effective way. Now let's talk a little bit about the solubilities, the relative solubilities of these carbide and nitride formers. This is the classic solubility curve for each of the primary microalloys: vanadium carbide, vanadium nitride, titanium carbide, titanium nitride, niobium carbide, niobium nitride, and aluminum nitride. As you can see, of all the nitride formers, the vanadium nitride is the most soluble. Niobium nitride is next, less soluble. Aluminum nitride is even less soluble for the most part than niobium, but very similar. And then you have titanium nitride that precipitates pretty much on solidification of the steel. It is extremely difficult to get back into solution. So what this quickly shows you is that you are at high risk. If you have any of the other microalloys contained in the steel along with vanadium, you are at high risk of losing that nitrogen to a competing element. So when you look at this strengthening model that we just developed, you can understand, you must say what nitrogen is truly available here. You have to look at the prior processing history and determine how much nitrogen is actually available to precipitate with the vanadium nitride, and from that then you can predict what kind of strengthening you might expect to see. Let's look at each of these elements specifically. We know that titanium nitride, that these can form at a very high temperature. It results in a direct loss of effective vanadium for vanadium nitride precipitation. And basically you can use a stoichiometric calculation of titanium nitride formation and presume that virtually all of that nitrogen will not be available and will not be part of the effective nitrogen available to the vanadium. The titanium nitride formed in the austenite does not provide strengthening. Virtually all of the titanium nitride forms in the austenite. It tends to be very coarse. It is not a strengthening size precipitate. Therefore, the titanium additions in a vanadium nitrogen system actually reduce the strength in proportion to the amount of effective nitrogen removed. They can be possibly an effective high temperature grain growth controlling precipitate, but they do not contribute to strength after the fact. Now, when we look at niobium nitride formation, we know it's less soluble than vanadium nitride or niobium carbide. Therefore, niobium additions will likely precipitate before certainly before the vanadium, and even to some degree before the niobium carbide, depending on the carbon level, of course. Higher nitrogen levels will tend to precipitate niobium at higher temperatures, removing niobium and nitrogen from solid solution. Niobium nitride will promote co-precipitation of niobium carbide and vanadium nitride in the austenite, which is where you do not want it to occur. So in general, nitrogen tends to reduce the effectiveness of niobium microalloying, although it can raise the T sub NR temperature if that's your desire. But most niobium alloy designs are optimized with as low as possible nitrogen rather than high nitrogen. Nitrogen combined with niobium in the austenite does not strengthen, and it will reduce the effective nitrogen level. And this incompatibility of niobium with nitrogen makes an efficient niobium-vanadium microalloying system somewhat problematic, because how do you use the niobium effectively and the vanadium effectively if in fact the niobium combines with the nitrogen before the vanadium, keeps it from forming vanadium nitride, which is what you want for strength. Meanwhile, the formation of niobium nitride actually reduces the effectiveness of the niobium addition in the first place as well. So this lack of synergy between the two is a major issue as we try to make these elements work together, and is something that we continue to struggle with. Here's some examples of the titanium precipitates as well as vanadium precipitates that Yuli and others have published. On the first graph on the upper left here just shows that in a CSP type operation where the ASCAS slab is equalized at 1050 C, that these precipitates quickly form, that they do not dissolve, and in fact, because of the pre-existence of the titanium nitride that forms on solidification, and then vanadium, it tends to co-precipitate vanadium nitride around those precipitates. Again, taking vanadium and nitrogen out of the system in the austenite where it will not be effective for strengthening. Similar things happen when you combine a niobium and titanium system. You get these precipitates here, somewhat lower magnification. So these are also relatively large precipitates that don't effectively contribute to strength, and they remove the microalloy that you've added from solution in the austenite, therefore not contributing to precipitation strengthening of the ferrite. Now, aluminum is also routinely used for deoxidation and meeting fine grain requirements on many of these steels. Aluminum nitride has a lower solubility than vanadium nitride, but aluminum nitride formation is very sluggish on the cooling process. Aluminum nitride does form quickly during a reheat cycle, so conditions during the process where you go through a cycle of cooling down and then reheating, such as you might on the slab surface during the casting process, or slab or bloom reheating during the, say, equalizing furnace in a CSP mill. All of those things are places where aluminum nitride might precipitate, and of course, if it does, it again steals the nitrogen away from the vanadium and is no longer effective for vanadium nitrogen strengthening. This is an example of aluminum nitride formation in a vanadium nitrogen steel and also in a vanadium titanium nitrogen steel, that the aluminum nitride will form, and at this point it's not contributing anything to properties. It does not provide a grain refiner because the grains are already large in this case, and it steals nitrogen away from the vanadium nitrogen system. Here's another example of the effect of aluminum on interfering with the vanadium nitrogen system. This is work done by Roth-Lutner and Van Tine, where they were doing forging simulations using a third base alloy of 37 carbon, 09 vanadium, and 15 nitrogen. and it had two aluminum levels they were looking at, a 006 and an 031% aluminum. They varied the forging reheat temperatures and times to get various amounts of aluminum nitride formation in the austenite prior to the forging and cooling step. And what they found was, as you can see on the graph on the right, is that as the aluminum nitride, as the amount of aluminum that precipitated increases, the amount of vanadium precipitate that occurred decreases. So in effect, it was a clear evidence of aluminum stealing nitrogen away from the vanadium and reducing the amount of vanadium precipitation that occurred, therefore lessening the vanadium nitride precipitation strengthening. In fact, they measured up to a 50 megapascal reduction in strength with the reduction of the reheat from simply reducing the forging reheat temperature from 1200 to 1100 C. We also know that aluminum nitride formation during casting contributes to cracking during unbending. Aluminum nitride formation can contribute to edge cracking in a CSP type operation where the first roll pass on a thin slab direct rolling process is actually trying to deform the as-cast austenite grain boundaries. If there's aluminum nitride formed on those grain boundaries, there will be a significant ductility loss. Aluminum nitride must be dissolved completely prior to rolling, which then increases the reheat requirements, which of course is a difficulty in a CSP mill. Even Grosser in Microalloying 75 pointed out that to get the appropriate strengthening from a vanadium nitrogen addition in a conventional slab operation, care must be taken that the slab reheat temperature is sufficiently high to get the aluminum nitrogen in solution. So any aluminum nitride formation in the austenite prior to transformation will reduce the effectiveness of the vanadium nitrogen strengthening component that you're looking for. So we know that aluminum does not contribute to grain refinement in the as-rolled steels, which is primarily where you use any microalloying system, is an as-rolled or as-forged. So therefore, adding aluminum to meet any fine grain requirement is in fact irrelevant and unnecessary. Yet it seems to be very common throughout the industry to request aluminum fine grain material, which in the as-rolled condition is in fact meaningless. And also we know that a minimum aluminum, say 020, is not always necessary to adequately deoxidize steels. In fact, the vanadium nitrogen system is widely used in the long product arena and where it typically is silicon killed and no aluminum is added. So we know you can cast steels with lower levels of aluminum than 020, or perhaps what has traditionally been accepted throughout the industry today. So the conclusion is that if you're using a vanadium nitrogen system and you want to be able to achieve strengths as predicted by this model that we are proposing, that you should minimize the aluminum additions so that you're only using that amount that's required for metallurgical reasons. And this includes, of course, primarily deoxidation, because grain refinement in an as-rolled ferrite perlite structure is mostly controlled by the process conditions, not the addition of aluminum. So at the end, we have this model that we propose should be used to best explain and to make the first level of prediction of what kind of strengthening you can get from a vanadium nitrogen system in a product that is hot rolled or hot forged and ends up in a ferrite perlite type of microstructure. Thank you.